All right, so now for our depth first party. So same exact graph, it's got 10 nice little vertices on it. We got this super well connected 6, this Kevin Bacon of vertices, and we're going to try to create these nice little spanning trees in this depth first fashion. So as before, I'm gonna start with the 0 just because it becomes a nice starting place. And if I were to see what is achievable within one click, I again have the 5, the 9, and the 8. So when I come over here to draw that out, I'm going to have the 0, which is then going to be connected to the 5, the 8, and the 9. So here I'm going to be putting them in kind of numeric order. So 5, 8, 9, organized from smallest to largest. Before we began in this kind of breadth first process is that I tried to search from the 5, and then search from the 8, and then searched from the 9. And then I went to the next layer. What I'm going to do here is I'm basically going to run it as far down as I can from kind of the last thing that was added. So this is this stack structure. The 9 was the last thing that got added here. So that's going to be where I'm going to search from. So the 9 is going to be connected to a 6 and a 7. I think in my notes I did this in green. So let's change that into green. So the 9 is connected to the 6 and the 7. The 7 being the last thing that I added is then going to be where I first start searching from. So from 7, I can't get anything new though. So it's kind of a bummer. It's like, hooray, you're first, and you can't do anything. So then I'm going to search from the 6. So from the 6, I can get pretty much everything. Oh, not if I erase everything. So I can get the 2, I can get the 1, and I can get the 3. So that's then going to get drawn like this. So I get a 1, a 2, and a 3. So then what's going to happen is that I'm going to search from my kind of last thing fed into this. So if I feed this in 1, 2, 3, my 3 is then where I'm going to branch from, and the 3 is connected to the 4, which is then going to be the end of my little party right there. You could then see that from the 2, from the 1, from the 8, from the 5, those don't give me anything new. So I would not actually have anything added on to this little graph other than what we have right there. So you try basically kind of backpedaling and see that it obviously doesn't work. So just like before, it does give us this idea that everything is actually connected. I can get to 0 to absolutely anything on this graph. This graph is completely connected. There's no weird kind of vertex hanging out over here that is unachievable. Everything in this network can actually be achieved. Everything is reachable. It's pretty easy to see the depth first process kind of unfold. You basically just kind of go really, really hardcore down one particular path as much as you can get out of it, and then you try something extra afterwards. So it's easy to implement, but it does come with kind of a downside, is that you can see that the 0 and 4 are obviously connected. What this tells me is that there's going to be a path of length 1, 2, 3, and 4 that connects them. So from 0 to 9, 9 to 6, 6 down to 3, and 3 over to 4. So it's like, cool, they are connected. I can get to them within 4 moves, which is not optimal because obviously I can do it in 2 moves. I can go over at 8 and down to 4. So what depth first kind of has in terms of ease of simplicity of design, it lacks in actually giving us questions to what is the shortest actual path. It's really easy to actually build this tree up really quickly, but it doesn't quite give us as much as that breadth first did before. But it's a little bit easier to actually design in that we just kind of go really hardcore down one particular path and then kind of try to dig ourselves out of that hole eventually. So there is that little caveat that I should mention is that, yes, it does show me that 0 and 4 are connected, but it doesn't tell me what the shortest path happens to be. All right, so we try doing another one just because depth first is kind of fun. Sure. We'll do kind of the dumb Kevin Bacon one just because it's worth seeing. I won't do quite the dumb Kevin Bacon one that I'm not going to start at 6. We'll do the slightly fancier version that we start at 1. And obviously from 1, you see that we are 1 click away from the 6. So if I draw this up, I'm going to have not a 0. I'm going to have a 1, which is then obviously connected to 6 within 1 move. And then from 6, we're going to basically branch out from there. So 6 is connected to the 2, the 5, the 9, the 7, the 8, and the 3. So if we draw those out in order, I'm going to have what? 2, 3, 5, 7, 8, and 9. That's a terribly drawn 8. And we'll get all those little tick marks in. All right, cool. So then my last thing would be to start my search process again. Where I'm going to search though is from the last things that were added. So the 8, the 9, the 8, the 7, the 5, the 3, the 2, so on and so forth. So from the 9, I can get to the 0, and from the 8, I can get to the 4. So those become the last things that I add in. And you can see that that actually creates my entire graph structure, is that I don't have to go searching for anything new after that because there's nothing left to discover. So from the 7, from the 5, from the 3, from the 2, there's nothing left to be found. So earlier I alluded to this idea that breadth first made use of this queue structure. Depth first is obviously going to make use of this stack structure. So if I have a list, here's going to be my S, my stack. What I want to do is I want to remove or begin searching from the last thing that was added into this. In Python, this makes use of this nice little pop function. So pop without an argument is then going to remove the last thing from that list. So if I hit s.pop, it's going to have that value 5. And then my resulting list S is then going to be numbers 1 through 4. So on D2L, you'll see a couple links to some implementations of these searching processes, basically what are questions of reachability. I'll do a quick video showcasing some of that, but they're really not that exciting. It's just like, here's my graph. It's stored as like, let's say a dictionary or a list of lists, and then let's have it just generate what's actually going to emerge from it. There's also a couple extra ones that you can create, the actual tree, which are, again, hopefully things you've seen before of like, hey, here's my original graph. It's got 20 vertices. Now let's create its spanning tree via some breadth first fashion. So go from the 0, go from these things, go from these things, and hooray, you get this cute little tree and it covers up what you're hoping it actually covers up. So hopefully kind of a nice quick review and kind of reminder of some of the notation and terminologies of some of these graphs. I've actually split this into 2 little sections. So in the second section on this, I'm still going to title this one Getting There From Here, but it's going to be version 2, which is all going to be about these adjacency matrices and kind of manipulating them in kind of a cleverish fashion as well. So stay tuned for more and all of the good 0-1 matrices and doing all of the work with them. So have fun, enjoy.